Section 11.2, Video 1. This section is on series. Again, like I said, for the sequences section, I believe that you will have already learned a little bit about sequences and series in a previous course, but we are going a little bit more in depth in this class. So series, unlike a sequence, actually means the sum of terms. A sequence is a list, if you'll remember, of numbers or of terms, and a series is the sum of those terms. So when we talk about a Riemann sum, if you were to list out those values and add them all up, you could also call that a series. Okay, so sort of an example to get us in the right frame of mind. What do we mean when we express a number as an infinite decimal? For example, they have pi written out to, I don't know how many that is, 30 or so decimals. So our convention behind decimal notation is something you might not remember, but it's the way you would have learned about it at the very beginning. Remember, we call the first decimal point the 10th spot, because you have 1/10, 2/10, 3/10, and so on. The second decimal spot is the hundreds spot, hundredth, hard to say that, sorry. 10 squared. The third spot is the thousandth spot, 10 cubed, 1/10 cubed, and so on. So as you go to the right out in decimals, the place is a power of 10. So we have 1/10 to the first, 1/10 to the second, 1/10 to the third, and so on. And that's how we identify what different decimal points actually mean. So if you wanted to write out the number pi as a series, you could do it with each individual digit from the way it's written here. So 3 is what it starts with as the whole number. And then the next decimal point is a 1, and that's in the 10th spot. So that's plus 1/10. 3 plus 1/10 is 3.1. What's the next decimal? It's 4, and that's in the 100th spot. So you could write that as 4/100. So 3 plus 1/10 plus 4/10 squared is 3.14. And that's actually how we typically talk about pi if we're not using our calculator. But as you go farther and farther out into the decimals, you can identify and notate each one with a division of 10 to the whatever decimal point that you're actually in. So I know this is sort of an unnatural way to write this number. However, it does show that we can take this number, this number with an infinite number of decimal points, and write it as a series. And then this is just making it clear, I think you guys know this, that the 3 dots at the end here means that it goes on forever. Okay, so in general, if we try to add the terms of an infinite sequence, meaning n goes towards infinity, we get an expression of the form a1 plus a2 plus a3 plus and on and on and on up until an, and then of course you keep going because it's infinite. If you try to add up all of these terms, we call that an infinite series. So if you have a listing of terms where there's an infinite number of terms, that's an infinite sequence. And if you're adding all those terms, we have an infinite series. So again, series means sum. And another way we can denote that series is with the sum notation, the sigma. So we have the sum as n goes from 1 to infinity of a sub n. Now, we've already used this notation several times when we were talking about integrals, so hopefully this looks familiar. But a way to write an infinite series is with this sum notation. It would be impossible to find a finite sum for the series where you just add up all the positive integers. But if we start adding those terms, we get larger and larger and larger values. And eventually the nth term is n times n plus 1/2, which don't worry about where that comes from right now, it's just given to you. But you can see, and you know that from what the sequence is to begin with, that that value gets huge as n increases. It's never going to converge to a stopping point. However, if we wanted to add up the terms of the series 1/2, 1/4, 1/8, 1/16, and so on, we would be able to denote that. Each term of this sequence is 1/2 to the n. And if we try to add all of those together as a series, we would start to get values that make sense. So what are these values? 1/2 is the first term. 3/4 is the first term plus the second term. 7/8 is the first term plus the second term plus the third term. So terms of a series indicate the sum of all of the terms up until that number. So the third term of a series is the sum of the first 3 terms of the sequence, if that makes sense. The fourth term of the series is the first 4 terms added up, and so on and so forth. So if you try to notate this, you actually can find a value to write it as 1 minus 1/2 to the n. Okay, and just to show you in a decimal format, because we're a little bit more comfortable with that generally, what these values look like, as n gets larger, the sum gets closer and closer to 1. So these individual terms of the series are called partial sums because they are a sum of terms in the sequence, but they are not the entire sum. They are just part of the entire sum, therefore we call them partial sums. So remember, n equals 1 in a series means just the first term. N equals 2 means the sum of the first 2 terms. N equals 3 means the sum of the first 3 terms. 4, the sum of the first 4th term, and then we add the 5th term, 6th term, and so on. And so you can see these sums are getting closer and closer and closer to 1. Okay, so in fact, if you keep letting n get larger and larger, we can see for sure that definitely those sums go towards 1 or converge towards 1. So we can probably say that the sum of this series is 1, and we can write it out that way. The sum of 1 over 2 to the n equals 1. Okay, so notation for a partial sum. We talked about what a partial sum is. It's a sum of the first however many terms of the sequence itself. And the way we identify those or notate them is with an s, a lowercase s. So S1 is the first partial sum, which is just the first term. S2 is the second partial sum, which is the sum of A1 and A2. S3 is the third partial sum where you add on that third term, and so on and so forth. So Sn, S sub n, would be the sum of the first n terms, which you could write with the sum notation with the sigma as the sum from I equals 1 to n. So the sum of the entire series would be I equals 1 to infinity, but the partial sum, Sn, you can write just from I equals 1 to n, so it has a stopping point. These partial sums themselves form a new sequence, S1, S2, S3, S4, and so on and so forth. And they may or may not converge. So if the limit exists, then we would say it converges, which is what this whole page is trying to say. If the limit of the partial sums exists, then the infinite series, excuse me, had to cough, then that series is convergent. And if that limit does not exist, of course, the opposite says that I'm sorry, I keep wanting to cough, that series is divergent. Okay, so the sum of a series is the limit of a sequence of partial sums. I'm going to say that again. The sum of the whole series, the whole infinite series, is the limit of the sequence of the partial sums. The sequence of the partial sums is a listing of the sum of the n number of terms. So remember, that's S1, S2, S3, S4, S5, and so forth. So whatever those values start to converge to would be the sum of your series. And we already saw this in that earlier example here. So we can see as n gets larger and larger, the sum of those terms is going towards 1. So the sum of a series is the limit of the sequence of partial sums. So when we write the sum of A equals S, meaning the overall sum from n equals 1 to infinity, we mean that by adding sufficiently many terms of the series, we get close to S. That is the final sum. And what we have written here is the sum from n equals 1 to infinity of A is the same thing in terms of notation as saying the limit as n goes towards infinity of I equals 1 to n. So this is just sort of a very tiny notation difference where you, instead of saying n equals 1 to infinity, you pull the n out into a limit, just like we did with integrals, and say I equals 1 to n. Again, we did this with integrals where instead of having an infinite sum, you pull the limit out, so you have a limit as n approaches infinity, but the sum itself is not necessarily infinite. And that is the end of the first video for section 11.2.